Okay, welcome everyone. In this lecture, we're going to study the third case of the second order constant coefficient homogeneous equations that we've been looking at starting last week. In this case, we have one double root of the characteristic equation. So let me remind you, we are studying equations of the form ay double prime plus by prime plus cy equals 0. And to study that, we look at the associated characteristic equation, which is a lambda squared plus b lambda plus c equals 0. And that's because we're thinking of looking for a solution of the form e to the lambda x. Okay. And so this is the characteristic equation. And that's a quadratic equation. So to solve it, you use the quadratic formula. So you get minus b plus or minus the square root of b squared minus 4ac all over 2a. And in the previous modules, we looked at the case where b squared minus 4ac is positive, and so you get two real distinct roots. We looked at in another video, we looked at the case of where b squared minus 4ac is negative, so you get two complex conjugate roots. And today, in case 3, we look at the case where b squared minus 4ac equals 0, so we get one double root, and that is lambda is equal to minus b over 2a. So clearly one solution is y1 of x is equal to e to the minus b over 2a times x. But we need, in order to write the general solution, we need a second linearly independent solution. And remember, when you only have two functions, you don't really need to know much about linear independence. It just means that you need a solution that is genuinely different. In other words, is not a multiple of this solution. So we can't do like we did in the case of two real distinct roots and say C1 times e to the minus b over 2ax plus C2. We can't say plus C2 e to the minus b over 2ax because that's the same solution twice. So in the reduction of order video, you found out that a second linearly independent solution, and let me use my abbreviation, linearly independent solution, is y2 of x, which is x e to the minus b over 2ax. Okay, and so by the reduction of order trick, we got the second linearly independent solution. So putting them together to get the general solution is now easy. The general solution is y of x is C1 e to the minus b over 2ax plus C2 x e to the minus b over 2ax. Okay, so that's the general solution. All right, so now let's look at a specific example. And this time we'll do one where we have some initial conditions. So let's look at the example, y double prime minus 6y prime plus 9y equals 0. And let's say y of 0 equals 1 and y prime of 0 equals 2. Okay, that's a y prime of 0. Make that clear to read, okay? So now in order to solve, it's a second order constant coefficient homogeneous equation. So we look at the characteristic equation. That means you replace the derivatives by multiples of lambda. Okay, so this lambda is going to, lambda squared here. First derivative becomes the first power of lambda, and the 0th derivative becomes the 0th power of lambda. Okay, And now this one's easy to factor. You see that is lambda minus 3 quantity squared. So lambda equals 3 is a double root. So you're in the case of a double root. As we just saw, then the general solution is y of x is equal to c1 e to the 3x plus c2 x e to the 3x. Okay, so you learn these things once you know the routine, and it's a double root, you know the routine. The other cases, you know the routine. Now we have to figure out how to satisfy these initial conditions. So we're going to need y at 0. That's easy to evaluate, but we're also going to need y prime at 0. So that means we're going to need to evaluate y prime. So when doing this for the initial conditions. Okay, so y prime of x is going to be 3c1 e to the 3x. Here I have to use the product rule, so I get c2 e to the 3x plus 3c2 x e to the 3x. Okay, and so now I use the initial conditions that y at 0 equals 1. On the other hand, y of 0 plugging into here with x equals 0 is equal to c1, because I get c1 e to the 0 plus c2 times 0. So that's just c1. So c1 is 1. Okay, and now y prime at 0 is equal to 2. So let's see, I plug in x equals 0 in y prime. So that gives me 3c1 times e to the 0 plus c2 times e to the 0 plus 3c2 times 0. So I have this equation, but I know that c1 is 1, so that says 2 is 3 plus c2, which tells me that c2 is minus 1. And so I can write down the explicit solution to this initial value problem up here. And the explicit solution is y of x is c1, which is 1, times e to the 3x, plus c2, which is minus 1, x e to the plus 3x, okay? And that's easy to verify that that's the exact solution to this differential equation, and it satisfies these two initial conditions. Okay, so that's all there is to the one double root case. But again, we built that from looking at the reduction of order case and knowing a little bit about linear independence and dependence, so we knew that we needed a second linearly independent solution. Okay, that's it for this lecture.